Okay, hello everyone. Welcome to the lecture 4 of the series of sensor and instrumentation. In the last class, we have seen that what are the difference between sensor and transducers, what are the how to classify the sensors, how to choose for a particular application depending upon the application, the sensors and the transducers. Then we came across how to measure the displacement parameter using different kind of sensors, in which we learned that potentiometer, LVDT, and optical encoders are some of the kind of sensor which is used for the displacement. Then we see that how to measure a force and a pressure, and what are the relation between the force and the pressure, where we use the term force and where we use the term more as a pressure. Now let's come across the another very important parameter in terms of when we are working in an industry, that is the measurement of temperature. Now temperature is a very important parameter when we work in an industrial, mostly in a chemical plants, mostly in a power plants, whether it's a petrochemical industry, whether it is a aerospace industry. The temperature is a very important factor to measure. So let's start with the what is the how the temperature has been measured using a different kind of sensor. So first analogy is to using a resistant temperature detector, that is RTD. RTD is a type of a temperature sensor that works by measuring change in its in the resistance. That is the if the metal resistance, if changes, the resistance increases linearly with the temperature. Now, what are the construction? How it is constructed? The temperature sensing element is typically made of platinum wire. Other metals are like nickel or copper can be used. The wire is wound into a coil or laid as a thin film and attached to a ceramic metal support. For example, if you see this is the standard platinum resistant thermometer, which is fragile and only used in a laboratory. And this is the platinum temperature, which is used thermometer and are almost as durable as a thermocouple. You see there is a outer coupling that is mostly the ceramic plotting material, like it cannot affect the inner core. Then we have inside where is a sensing element, that is mostly the material that has been that you are using, like here we use a platinum core, some of times we use a nickel, some of time we use a copper also. So this is the construction of a very standard RTD. Then we have the assembly is placed inside a protective probe, that is a tube often made of a stainless steel or safeguard it against a mechanical damage and the environmental effect. So in industry, maybe there is some ruggedness. Due to some ruggedness, there are some chemicals also which can affect the platinum metal or the inner core. So we mostly use a material that is that is chemically inactive. For example, like stainless steel, or we used as a ceramic material for the outer coating, because it has not been chemically very active. So leads are connected to the sensing element, allow for electrical measurement. Then electrical resistance of certain metal changes is known and predictive manner depending upon the rise of and fall in the temperature. When the temperature rises, the electrical resistance of the metal increases, as we know. And then as the temperature drops, the electrical resistance decreases. So RT uses this characteristic as a basis of measuring temperature. The sensitive portion of RTD is called an element. Is a coil of small diameter, highly purity wire, usually constructed of platinum, copper, or nickel. This type of configuration is called wire-wound element. With thin film element, a thin film of platinum is deposited on a ceramic substrate. So standard platinum resistance is SPRTs, the highest accuracy platinum thermometer, are fragile and used in a laboratory environment only. Fragile materials do not provide enough strength and vibration resistance for industrial environment. SPRTs features high repeatability and low drift, but they cost more because of their material and expensive production technique. So this is a standard thermometer which is fragile and used in a laboratory environments mostly. And this is the industrial platinum resistant thermometer, almost as durable as a thermocouple that we already told you. Now, this is the standard. If you see in an industry, this is the image of a real image of a industrial platinum resistant thermometer that is almost durable as a thermocouple. You see, this is the sensing element, this is the sensing element, this is the protective tube, and this is the connecting heads, and this is the fitting. So you can connect whatever the signal processing unit you are connecting through here. Since RTD is a passive kind of transducers, or you can passive kind of transducer, so you need a external power supply to make it work. So whatever whenever and it is a contact type of sensor. Contact type means you need to be in a physical contact with the source of which you are measuring a temperature. Suppose it is a chemical, or it is some kind of liquid that you are measuring. So it should be in contact to that particular area or source. So this is RTD. And second, all it is it works on a positive temperature coefficient of principle. Like, as the temperature increases, the resistance is also increases. So according to the formula, R is equals to rho L by A. So this change in resistance has been detected. So if there is some change in the temperature due to which the length has been changed or area has been changed, suppose there is a change in the length. So if length has been changed, so we have a delta R is equals to rho delta L upon A. A is a constant. So this can be changes, and due to this changes, you see, we can use it in a Wheatstone bridge or something like that. In a Wheatstone bridge, if one resistance changes, then you can put it here, the thermist RTD, and due to delta R, there is a change in the delta V. So this is how the RTD has been used in an industry, or to measure the change in the temperature. Now, what are the working principles? I already told you. Operate on the principle that metal increases their electrical resistance is nearly linear fashion as the temperature rises. When metal is heated, its atom vibrate more, making it harder for the electron to pass through, which raises the resistance. By passing a small constant current through the wire and measuring the resistance, the temperature can be precisely determined. In operation, the measuring instrument applies a constant current through the RTD. As the temperature changes, the resistance changes, and the corresponding change in the voltage is measured. This measurement is then converted to thermal values by the computer. Curve fitting equation are used to define. Now, working. How temperature is measured? RTDs are connected to the Wheatstone bridge circuit or specialized electronic instrument which interpret the change in the resistance as a temperature value. Depending on the number of wires, 2, 3 or 4, errors from lead resistance can be compensated for 3 wire. So is most commonly in industry for the high accuracy working, how temperature is measured. In the most typical arrangement, RTD are connected to the Wheatstone bridge, that is, I already told you, for the specialized electronic instrument, and interpret the change in the resistance as a temperature value. Depending on the number of wires, 2, 3 or 4, errors from the lead resistance can be compensated for 3 wires is most commonly in industry for higher accuracy. So this is how we can use the RTD. Now, if you see the input-output relationship in terms of industrial parameter, you should know what is the relation, what is the characteristic. So input-output characteristic is the relation between the input and the output. For example, if we see the RTD means the resistant temperature detector, the input is the temperature, because there is a change in the temperature that has been detected, and the output is the change in the resistance, that is delta R, delta T and delta R. So this is the temperature, it has been increases this way, and this is the resistance in ohm, in degree centigrade. So you see, we have three materials that has been used as a sensing element in the RTD, that is a platinum, copper and nickel. You see, the most linear one is the copper, but since copper has a very limited range, because it cannot be measured more than 400, 300 centigrade, and in the its range is very short. So depending upon if your range is within the range of the copper, then you can use the copper. Then you see nickel and platinum has been very much linear in some range, but not in whole, as you see. But platinum has a very wide range. So you see, platinum is a range in a minus 200 degrees centigrade to 850, up to 850 degrees centigrade, which is a temperature you can go in industry, but mostly in industry. Then nickel is minus 200 to 260 only. Copper is from minus 80 to 300 only. So you see, the range is very much affected whenever the application is whatever. Obviously the platinum RTD is way more costlier than nickel and copper, but if you have an application where you need to be more linearly, you need the input output relationship to be linear, and you working up to that kind of range, then you can surely go for the platinum RTD. Now if you see the relation, then RT is equals to, which is the simple linear relation of the temperature coefficient, that RT is equals to R naught 1 plus alpha into T, whereas alpha is the temperature coefficient. For platinum it is approx 3.85 milli whatever say per degree. It does not has a unit per degree centigrade. Platinum is widely used element for RTD due to high stability and accuracy. And for example, RTD has a, if you see for a calculation, if RTD has a resistance, that is, what is 100 degrees centigrade, that is R naught at 100 degrees centigrade. It is 100 ohm, sorry, it is 100 ohm at 0 degrees centigrade. Okay, and the temperature coefficient is 0.35, that is alpha is equals to 0.385. Here we already, it is ohm. Okay, ohm per degree centigrade. Then calculate its resistance at 100 degrees centigrade. It is a very simple formula where you can use that RT. Use this formula, RT is equals to, when we use, that is R naught is equals to 100 into 1 plus 0.385 into delta T. Delta T means from 0 to 100 degrees centigrade, it is 100. So whatever the value is, 100 into 0.3, that is into 39 39.5, and whatever the value is, 395 ohm. So this will be the answer. Next, what are the advantages of RTD? That is high accuracy and stability over time, obviously, excellent repeatability and linearity, wide but moderate temperature range. It is wide, but still it is very moderate when we are dealing with the industry where the temperature can go up to 2000 or 4000 degrees centigrade. It can be, the boiler temperature can go up to the 1000 degrees and 1000 or 1500 degrees centigrade. So chemically it is very very inactive and robust in industrial environment. Disadvantages: it is expensive, especially in a platinum foam, slower response time than a thermocouples or thermistor, require excitation current leading to possible self-heating errors, limited to moderate temperature ranges. Application is process control, food industry, pharmaceuticals. Now other application that I already told you, power plants, HVAC systems, that high voltage AC systems. Then scientific laboratories, anywhere precise stable temperature monitoring is required. Then we have this kind of systems. Then measurement of temperature using thermistor. Definition: a thermistor is a temperature sensitive resistor made from a semiconductor material designed so that its resistance changes rapidly with temperature. Most commonly NTC, that is negative temperature coefficient. Thermistor decreases in resistance as temperature rise, also known as thermally sensitive resistors. Now this is the another kind of sensor which is known as the thermistors. Now thermistors have NTC kind of material. Thermistors have two types. We have a thermistor also. We have a thermistors also. Thermistors are like they are NTC kind of material. NTC matlab means negative temperature coefficient means as the temperature increases the resistance decreases, because mostly thermistors are made out of a semiconductor kind of material. That is why. So thermistor is a temperature sensitive resistance made from a semiconductor material designed so that resistance changes rapidly with temperature. Now mostly NTC, thermistor decreases temperature as temperature rise, also known as thermally sensitive resistor. So sometimes it is known as sensistors also. Sensistors, not sinister, sensistors. Made from a compressed and sintered oxide of metal like manganese, nickel, cobalt and copper, formed into a beads. These are kind of the structures. We have a bead kind of thermistor. These you can see mostly in laboratories, in academics. Then we have a disc type also. Then we have a rod types also, usually encapsulated in a epoxy resin or a glass for protection. Material used are for sensing elements, various metal oxides, ceramics, and for encapsulation, glass or epoxy. Now, what are the working principle? Already told you. Based on the semiconductor properties, a small change in a temperature causes a significant change in electrical resistance. Now, in NTC type, what happened? Temperature drops as temperature rises. Resistance drop as temperature rises. It consists of metal oxides such as oxide of chromium, cobalt, copper, iron, manganese, nickel, and titanium. You see, all these temperature sensors uses Wheatstone bridge for a signal processing circuit, because there is a change in the resistance, and due to change in the resistance you should have some value which due to which there is a from the change in resistance you got a voltage. Okay. Now PTC type, resistance increases as temperature rise. It consists of compound of barium, lead and strontium detonates. Working, how temperature is measured. A bridge circuit or a voltage divider is used in a conjunction with a thermistor by passing current and measuring voltage. Temperature is informed from the resistance using a pre-calibrated tables because the response is non-linear. This is the input-output relation of a thermistor. You see that PTC is mostly in this kind of range, that as the temperature increases, the resistance is also increases. But NTC is like opposite. When the temperature is less, the resistance is high. But as the temperature increases, the resistance is decreases. So it follows another principle, that is where the relation is RT is equals to R naught e की power 1 upon beta T1 minus T2. So mostly it is RT2 upon RT1. Okay, so this is like, so R is the resistance at temperature T and R naught is the resistance at temperature T naught, and beta is the constant. So a thermistor has a resistance of like 10 kilowatt at 25 degrees centigrade. Calculate the resistance of the thermistor at 75 degrees centigrade, given that at 3500 degree Kelvin. Beta is a 35. It is in mostly when we are dealing with the thermistor, we mostly use do not use degree centigrade, we use degree Kelvin. Okay, so what are the advantage of thermistor? It is a very low cost, high, because we are using a semiconductor material. So semiconductor material are mostly low cost materials. So it is a low cost, high sensitivity, fast response, very compact, easy to use. What are the disadvantages? Advantages: limited temperature range. Its range is very low, that is minus 80 to 150 degrees centigrade, not more than that. Non-linear output makes scaling and calibration more complex. the characteristic is non-linear. So obviously, when you are dealing with the non-linear systems, there are some constraints are there. Can self-heat, potentially affecting accuracy, less rugged than the RTD or thermocouple. So mostly it is a non-contact type of material. So whenever like it has a very high sensitivity. So whenever you are constantly monitoring the environmental temperature, you can use the thermistor. So application is electronic thermometer, thermostat sensors, appliances like air conditioner, fridges. They have because the sensitivity should be very high for temperatures, like very slight change in the temperature should be detected in thermometers and in refrigerator. So we use the thermistor there. Battery temperature management, we use the thermistor. Inrush current limiter, over current protection, we use a thermistor. So it can be used as a switch also, thermal switch. Automotive electronics. Now definitions, we move to another temperature sensor, that is a thermocouple. Thermocouple is a very wide range of it's a very high linear and highly linear, high range, everything. So it is mostly built for the industrial purpose only. So a thermocouple is a temperature transducer formed by joining two dissimilar metal wire at one end called the hot junction. When this junction is heated, a voltage called Seebeck voltage, it basically work on the principle of Seebeck effect. So a Seebeck voltage has been produced and that can be measured and correlated to the temperature. So it is a kind of active transducer. Active means you does not need an external power supply here. Now construction is two wire made of different metal. Like we have the two wire should have some kind of relation. So you cannot just make two different metals. So two dissimilar metals should have been there's a couple like we can use copper constantine, then iron constant, then chromel aluminum jet at one end and hot junction. The other end cold or reference junction are connected to measuring instrument. Often encased in a protective shell, that is a stainless steel or inconel, possibly with insulation. So this is the construction you see. We have an insulation here, we have a hot junction here, there is a different junction here, and there is a compensating lead of copper wire. So you have to connect different metals, and the outer shell has been like a metal sheet or anything insulation material is there. So the working principle, it relies on the Seebeck effect. When two dissimilar matter are joined, a voltage developed at the junction proportional to the temperature difference between the junction. The greater the temperature difference, the greater is the thermoelectric EMF produced. Now the thermocouple produces a voltage that is non-linear related to the temperature. Reference tables or polynomials are used to convert the measured voltage to temperature. Cold junction compensator is required since the sensor actually measures the temperature difference. So this is the working principle. Suppose you see some temperature rises here at the sensing point, and due to the dissimilar method, there is a one voltage has been developed which is known as Seebeck voltage, and it has been developed here, and it can be measured through the voltmeter. Now what are the input output relationship? It is a very much non-linear, time dependent, but for some range it is show a linearity also, where V is the EMF in millivolt, V is equals to S minus S into T hot minus T cold, where S is the Seebeck coefficient. So every relation or every couple like wire material like copper constant, we say that it is a type T. For every metallic combination, we have named the thermocouple. Like for type J, it is iron and constantine. For type K, it is aluminum and chromel. For platinum, rhodium and platinum, it is type S or B. Then it is sheet insulation, stainless steel or inconel or ceramic. So we have type K, type J, type T, type E, and for depending upon that combination we have the temperature range. So you see it is up to 1260 or more than that. Some combination can go up to 1500 degrees centigrade. Now, what are the advantages? Very wide temperature range up to 1800 degrees centigrade or higher, time dependent, rugged construction suitable for harsh environment, low cost, fast response time. Disadvantage, low accuracy, prone to drift over time, non-linear output, reference junction, that is cold compensation, is always needed, prone to EMI, required shielding, amplification in noisy environment. Now, application is industrial furnace and boilers, steel and metal processing industry, gas turbine and engine exhaust measurement, and domestic gas appliances. Now, how to differentiate that which temperature sensor should we use? Now, based on the principle, RTD uses metal resistance increases, thermistor uses semiconductor resistance, and thermocouple uses seebeck EMF from the metal junction. It does not use the change in the resistance. Construction bases, biofilm on core, ceramic bed, this encapsulated 2 different metal wire joint. Range is minus 200 to 850. The thermistor is minus 80 to 150. Thermocouple is minus 270 to 1800. Accuracy, RTD is very high accurate, thermistor moderate high, and thermocouple is very moderate. Outer behavior, RTD is very linear, thermistor non-linear, strong non-linear, and thermocouple are non-linear in millivolts. Response time, moderate, thermistor is very fast, thermocouple is very fast. Cost, RTD is very high cost, thermistor is low cost, and thermocouple is low to moderate. Application, highlights, RTD when precision is needed, thermistor when electronic appliances like where sensitivity is needed, thermocouple when industry or high temperature is needed. So let's make to the thermal imaging. The another concept, thermal imaging basically depending upon the infrared sensing, like as you see, as the frequency increases, our wavelength is decreases. So based on the this concept, that is electromagnetic spectrum, we see that as we move towards the lower frequency, the temperature has been very much decreasing, and as we move towards the high frequency, the temperature is basically increases. So the thermal imaging is a technology that detects the visualizes temperature difference by capturing the infrared radiation emitted by the object. Every object emitted, in fact, my body is also emitted some kind of radiation, and which has been detected by the thermal imaging sensors. So it's allowing the creation of images based on the heat rather than a visible light. So concept of thermal imaging operates on the principle that all objects above absolute zero emit infrared radiation as a function of their temperature, unlike conventional cameras that use visible light. Okay, and thermal infrared band, the optimal waveband for thermal imaging is determined partly by the wavelength distribution of emitted radiation, partly by transmission of atmosphere. The power radiated from a given area of the object depends only on the temperature and the nature of the surface world. So if the body absorbs all the wavelength, it is called as a black body. Now it is also emits the maximum amount possible, which can be calculated using a planned equation. At wavelengths above 3 micrometer, this is generally inefficient energy emitted to allow thermal imaging. So the emissivity, is known as the whatever the ratio of the energy emitted by the wavelength, the energy that would be emitted by the black body as the same wavelength and the temperature. So E object upon E black body. Now here we stop. Thank you for today.